In this example, for area between two curves, both curves are given in a non-standard form. That's their x in terms of y. So we've got x equals 3 minus y squared and x equals y plus 1. So to graph these, we'll have to solve for y, at least to use our calculator to help us, or just so that we're comfortable with it. If we subtract, so this ends up being what? Y squared equals 3 minus x, and this is y equals plus or minus the square root of 3 minus x. And our second curve will be y equals x minus 1. When we graph these, just to get a sense of what they look like, here's the line x minus 1. It's doing something like that. Y equals the positive square root of 3 minus x is a curve that looks something like this. That's the positive square root. And the negative square root of 3 minus x is a curve that looks something like that. So what we'd like to find is the area right here. So in terms of x, we need to find this point of intersection, this point of intersection, and that point of intersection. If we were to find all three of these x values, points of intersection, we could do some things. So let me just mention how you could approach this in that way. We'll call this x value A, this x value B, and this x value C. So notice, I'll add this in red, that this is really two sections. In our first section, we would integrate from A to B. Our upper limit of integration, our upper curve, is x minus 1. And our lower curve is the negative root of 3 minus x. Right, and that gives us this area to the left of the red line. We'll want to add to that the integral from b to c, and our upper limit of integration is the square root of 3 minus x, and our lower limit of integration is the negative root of 3 minus x. And in both cases, we're integrating with respect to x, so dx. So some things to notice. Our equations are in terms of x, our limits of integration are x values, and we're integrating with respect to x. Right? So there's some consistency everywhere. We can do it this way. But the way this information is given, it's easier to think about, or another way to think about it at any rate, is in terms of y. Right? That we could integrate from here for this y value to here. I'll do it in blue. From here to there in terms of y values. Right, so let's just first get those points of intersection, and then we'll talk about how to think through what our upper curve is in this case, because we're thinking about the equations differently. So first, we'd like to know, when do our two equations in terms of y intersect? When does, change back to black, y plus 1 equal 3 minus y squared? Well, if we solve this quadratic, we would find that they intersect at y equals negative 2 and y equals 1. So that alone tells us our limits of integration in terms of y. Now, when everything was in terms of x, our upper limit of integration was always the one on top, the one that was more positive vertically. And that should make some sense because the y-axis gets more positive as you go up. If we're thinking about things in terms of y, the one that is more positive is the one that's more to the right horizontally. So in this case, the one that's more to the right horizontally, I'll outline it in green, is this curve. It's more to the right horizontally than this dashed line. And because we're thinking about this, or can think about it at any rate in terms of y, we only need one integral. So we'll integrate from right to left. In this case, our rightmost curve is 3 minus y squared minus our leftmost curve in terms of y plus 1 dy. And again, notice the consistency here. Our limits of integration, -2 and 1, are y values. Our curves are in terms of y, and we're integrating with respect to y. I'm going to clean this up just a little bit before I integrate. I'm still going to integrate from -2 to 1. My curve is -y squared minus y plus 2 dy. And when I integrate that, I end up with -1/3 y cubed minus 1/2 y squared plus 2y from -2 to 1. Substituting in 1, this will be -1/3 minus 1/2 plus 2 minus, substituting in -2, this will be 8/3 minus 2 minus 4. And simplifying everything down, my area is 9/2 units. Right, so it just gives us another option, a way to think about finding the area between two curves. Our final example for this section is, in one sense, a fairly random problem. Let me set it up. We're given these 3 points, 2, 5, 0, -3, and -2, 1. So here's 2, 5, 0, -3, and -2, 1. These points form a triangle whose area we need to find. Well, the method that we'll do in order to find our area, I'm just going to explain the method, is we need equations for each of these lines. So there's the first line that make up the lengths of this triangle. Once we have equations for those lines, we can look at their points of intersection, here, here, and here. And we can see for our first integral, our upper limit of integration will be this portion in red, from this x value, which is -2, to that x value, which is 0. And our second integral will be this portion of our line, and in my case, this line, from 0 to this point of intersection, which is 2. So let's have two integrals using the same idea to find the area of a triangle. So that's all for the area of a region between two curves.